video podcast for Chapter 2 of Field Methods in Hydrology, which is going to be about geographical positioning methods. This is the first video podcast where we're going to look at the actual ways to measure something in the field that's relevant for hydrology. And really, when you're talking about anything related to the Earth's surface or even in the atmosphere, you have to know where you are in the world. Sometimes you just need to know where I am relative to something else, like how far away you are from something. Or other times you need to know, okay, within the UTM coordinate system, I'm at this northing and this easting. So there's a wide range of things you might want to know, and there's a wide diversity of technologies that are available to do that. And we're going to look at that, and then we're going to practice in class using some of these different technologies. Sometimes you're collecting this kind of data because you just want to see, okay, I've got 10 different sites. Well, where are they relative to each other? And maybe distance is the most important thing to know. On the other hand, maybe your sites are overlaid on top of a world that has topography or other spatially variable conditions, different rates of precipitation or densities of the soil. And so understanding how your variable of interest is influenced by another variable that is not randomly arrayed but is spatially explicit is important. And so then you're going to want to know these spatial positions. In this class, the emphasis here is on field methods. That means I'm going to be giving you the nitty-gritty of how to actually measure things. And to do that, what I have to show you are all the different technologies that are available, because for any one way of doing something or piece of information you want to know, there's many different ways of collecting it. So what I need to do is I need to describe to you what the technology is. I need to list the things that make that particular approach beneficial to you. There are always going to be things that are limiting or detrimental about an approach. We'll call those the cons. And then finally, the most important thing is when you're a professional hydrologist, you're going to have clients who only have a certain amount of money or only have a certain amount of need. And so being able to map the specific approach to use to meet just what is necessary, not always getting like the Rolls Royce of measurement, but just what is necessary to achieve the goals that you have, to the right accuracy and precision for the problem at hand. Of course, when we're talking about a hands-on piece of equipment, just hearing it in a lecture only goes so far. And that's why for this class, we have a very strong in-class component as well as playing in the laboratory with equipment and then going out on field trips and really putting them to use, because that's how you're really going to come to appreciate the pros and cons. But I think hearing first in a lecture, playing with the equipment, and then refreshing yourself on the lecture again helps you to put it all into context to appreciate how something works, not just in theory. Also, some video podcasts, I'm going to have to present a little bit of the theory behind a technology, like if you want to measure velocity, well, where you go and do that and how long you measure something for are all dependent on the nature of velocity, of how water moves. And so we have to say a little bit of it, but we don't want to go too far rehashing stuff you've learned in other hydrology classes. Okay, well, in terms of geographic measurements, one of the big issues that comes up is deciding whether you need to know, whether you need to know where in the world something is or just its relative coordinates. Relative means, this point that I have relative to another point, like how they are connected to each other, but not necessarily knowing I'm in a particular coordinate system. So for example, if you look at this slide on the screen, I've got this red point off on the side and it says, where am I? I'm just a point out in the middle of the world. I don't know where I am. And let's say that I were to have another point not shown, but let's say I'll put the arrow over here. Okay, if I want to know where the red dot is relative to the black arrow, then I either have to measure a distance between them and just be satisfied to say, hey, I don't know where I am, but I'm 5 feet away from this other thing. Or you could say, gee, I really want to know where they are. And to do that, you have to have a coordinate system of some kind. Coordinate systems come in a wide variety of types. They could be spherical coordinates, cylindrical coordinates, radial coordinates, or just a simple Cartesian planar, two-dimensional or three-dimensional planar coordinates. So here, for example, I've got the red dot located within this coordinate system. I know its location, 2.5 and 2. Okay, that tells me something really important about that point. However, just knowing the point isn't always enough, because I often need to know a direction. So in this case, I need to know that if I go in this up direction, that I'm going along the y-axis alone, and if I go to the right or left, I'm going along the x-axis alone. So usually, to put your point into a coordinate system, you have to know the position of a point and what is an orientation or direction that you're facing relative to where the coordinate system is. So for this to happen, a coordinate system has to have something called a datum. Datum is basically the 0, 0. So in the Cartesian coordinate system, we have a 0, 0 datum. Now we can put that anywhere, and we just know that this point is relative to that. But in the real world, we have real datums. I mean, whether it's time, we have like Greenwich Mean Time, or we can have 0 positions in a latitude and longitude, or in a northing and easting for different, say, state plane coordinate systems. So you have to pick something. Where you pick to be your datum can be arbitrary, but it's just we all have to agree on where that is. And so here in the United States, we have the National Geodetic Survey to help establish that and coordinate to get everybody to use the same thing and keep everything up to date. So if you want to learn more about that, I suggest you look at the website for the National Geodetic Survey. Typically, as an individual hydrologist, you can just find out where are local benchmarks in your area and get the coordinate values for that. And then also it will tell you what coordinate system and what datum is in use. Okay, so let's start working through the specific technologies. I always like to start with the cheapest, simplest methods. These give you the least amount of information, but they're very fast. Of course, I'm sure you're all familiar with a tape measure. It's a device for manually measuring distances using a graduated string of some kind made of metal, rope, cable, fiberglass. Typically, it could be as small as a ruler, so 1 foot long, to hundreds of feet or meters long. But of course, the longer it gets, the more difficult it is to manage it. There are other kinds of tape measures like wheels that you roll, and as you roll, it clicks every meter or something like that. So generally, you have 2 locations, and you want to measure a distance between them. Preferably, these are locations along a line, so you don't have to worry about any kind of turns. So the nice thing about a tape measure, it's cheap. You just go to a hardware store. You can buy either the simple contractor's type of tape measure shown in the top, or more of a field scientist tape measure shown on the bottom. They're very lightweight and easy to use. All of us learn how to measure things in elementary school. On the other hand, it can handle turns. It cannot really work within a pre-established national coordinate system because you have no way to ensure that you're moving right along a one-dimensional axis. So it's really a one-dimensional measurement tool, and so it has some limitations there. The next step up is kind of a big leap, but it's a relatively straightforward tool to use. And I promise we will be using these different technologies in the field, and you'll get a lot better feel for how they work when we go and do that. So this device is called an auto level. An auto level is a device for measuring heights. It can also measure horizontal angles and distances, but it doesn't have a vertical axis. It's just on a horizontal plane, so it can't measure any angles in the vertical, so that has some limitations. So here's one example of how you might use an auto level to understand how it works. The first thing you do is you set up a tripod. It doesn't really matter where you set it up, and you do not set it up on your benchmark. That's the important thing. Then you have at the top of a surveyor's tripod is a flat plane, a flat metal surface, and we usually these little wheels called screw jacks, and we can use those with a little air bubble in water that's built into the tripod or built into a base unit, something called a tribrac, Tribach, and that's part of an auto level usually. That lets you get it completely horizontal, and you'll get practice with this, so if it doesn't make sense, don't worry too much about that right now. So you get the tripod horizontal, so it's flat, and then you put the auto level instrument itself on that. And so now you can measure distances and angles on that horizontal 2D plane. Then you have another person come along, and this is going to be the rod person. And in many ways, the rod person is the one who has to do the intelligent thinking to decide what to do. Now, in this one example, this is showing measuring a channel cross-section, but it doesn't have to be. Usually, an auto level, like you could use this very easily to measure a profile, two-dimensional profile, such as this cross-section of a river, but it could be the slope down a hillside, for example, or the slope of a road. So that's really the two main things that we use an auto level for, is to measure profiles, which can be cross-sections or longitudinal profiles, and so those are giving the shape, which could be a slope or more complex geometry. So in this case, you can see that there's a pin set up on either side of the bank, and then a measuring tape is put across that with graduations at set intervals. And so what happens is that you start off with the rod on one bank, say next to the pin, or either at the 0 point or just the very first horizontal measurement position. And the person at the auto level sights through the telescope. It kind of looks like a binocular or telescope. You look through that, you focus up on it, and you just read the number that's on the graduated rod. You can see in this case where we're on the riverbed, the position is pretty much near the top of the rod. The numbering starts at the bottom, so it goes 0 and then it graduates up to the highest number at the top. What that means, and this is a harder thing to visualize, so this will be something that you can practice in the field, but here the surveyor is at the lowest location in the channel bed, let's say, and the number is going to be a very big number. So let's say this is number, 8 out of 10, whatever units they are. Now when the person comes up on the bank and you go to that same horizontal position, well, since they're up, the rod is going to be up higher, which means that the telescope will be reading off a number closer to the bottom. So actually, the higher the ground is, the smaller the number will be. So that's how it works in practice. I know that's kind of a hard concept, and it's one of those things that you'll get instantly as soon as you start playing with it in the field. The important point is that as you go across in fixed increments, you can rely on the tape measure to give your distance, so that's still a value of a tape measure. The auto level also has a technique to measure distances if you're moving in line with that. So here you can see we're straight in line, so we could get the distances using a technique with the auto level that we'll practice in the field. And you just read the heights, and this person holds the rod. This person will be reading the values and either writing it down themselves or calling out to a third person who could be keeping track. So even though the auto level is sort of automated in some fashion, it still typically involves manually writing everything down. The cost of an auto level depends on how good the glass optics are in that. It also might have some bells and whistles or automated software, hardware features to it, but typically a reasonable auto level could be in the $200 to $700 range. Whereas really fancy one might be as much as $2,000 or more. So the advantages of an auto level, it's relatively inexpensive compared to the technologies I'm going to show you next. It's very easy to use. Just takes a little practice, 20-30 minutes, and you pretty much got it down. And it's the best method for just determining relative elevations along a line. So depending on how precise the graduation is along the rod, and if you're close enough to accurately read that, then you can really well tell what your positions are. Some of the disadvantages, well, this is not a good method for making three-dimensional topographic maps. It can turn horizontal angles. You can measure height changes and distances, but you would have to do a heck of a lot of manual computation that way. It's really not designed for that purpose. Also, if you want to establish working in real-world coordinates, it doesn't matter where you set up here. You just have the survey rod person position themselves for the first or last measurement, somewhere along the way, measure right on top of a benchmark, and now you know an elevation. So if the benchmark is 300 feet above sea level in the NGVD88 coordinate system, let's say, or datum, then you can say, okay, I'm at 300, and then everything would be relative to that. So if you have benchmarks nearby, you can survey in an absolute Z coordinate system, but that is not usually the case. Like, the main advantage of the auto level is really easy to just throw it in a backpack with a rod, hike up into the remote mountain somewhere, and be able to make measurements wherever you are with really efficient setup time. The next step up goes to the total station. In my mind, I love the total station. It's a great instrument. In the old days, 20 years ago, 10 years ago, the total station was somewhat of a beast. It could just straight up a device to measure distances and angles, but you might have to write all those numbers down in a notebook and then do all the computations back on your desktop computer. So when I was doing my PhD in the early 1990s, I worked with a civil engineer. And that's what they did. They wrote all that down, and there was a lot of room for error. It was really challenging. It's basically a question of just being very anal and precise, and just trying to be as thorough and careful as you can. Today, a total station is a very different kind of machine. It's highly automated. It can turn on its own. It can measure everything without much human interaction. It's a much more straightforward process. Nevertheless, it does have a steep learning curve, so it helps to really get some practice understanding the fundamentals so that you use it properly. So again, it's a device that you set up on a tripod. You can see in the photo here, and just like with the auto level, you have to set it up in a way that gives you a horizontal plane. So we use the screw jacks and the legs. Now, ideally, we often want to set this up over a known benchmark, and that can be a time-consuming process. But you don't have to. There's many different ways to initiate a survey with the total station. You could set it up on an arbitrary point, call that point 100, 100, 100 for X, Y, Z, and give it a direction, say, hey, arbitrarily, this way is north, and then off it goes. If you don't need to tie into a real-world coordinate system, you can just sort of make stuff up in a relative local system and go. And again, like the other methods, this is one that we're going to play with in the field, so a lot of the ideas that I'm talking about will make a lot more sense when you're playing with it, but it helps to get a little bit of an introduction first. So typically we might set this up on a known point, and then what we're shooting to in this case is not a graduated rod where we have to manually read off a number, but there's usually a mirror on a stick. And in this case, the stick is on a benchmark being held fast by a prism pole tripod. So what happens is that typically a infrared light is shot from the total station to the prism, and then it reflects back. And based on the time it takes to make that traverse, you get the distance, because we know how that wavelength of light moves through the air at a typical temperature and atmospheric pressure. And so you get that distance. In addition, the total station can rotate up and down and left and right, so it can keep track of those vertical and horizontal angles. A really good total station is called robotic. So if you keep a prism facing the station, as the survey rod person moves around, it will just track you. And this could be entirely a one-person operation where you've got a little handheld computer called a data collector, and as you are, you just attach that to the rod, and as you walk around wherever you want to take a shot, you just push a button, and in like 1 second or less in some cases, you can get a shot. So the total station is extremely fast. when done with precision, like, very close attention to detail, it's the most accurate method of three-dimensional mapping that exists, that I know of. It's accurate to the millimeter or centimeter level, and again, relative to the time it takes. There may be other things that you could, do in a slower fashion, but in terms of just the raw speed, I mean, we can be out in a landscape, especially if it has fairly open terrain, and as fast as you can walk, you can be mapping topography. So it's very, very good. Another thing about a total station is it has a lot of software built in to do a lot of different tricks that surveyors need. Usually for Earth kinds of observations, we don't take advantage of that. We don't really need it. But if you go in a civil engineering direction, you might use that. The biggest disadvantage of a total station is the steep learning curve associated with it. It does take time to learn. I would also say just total stations are prone to human error. If you let your guard down for 1 minute, all you have to do is measure this prism rod wrong, and your whole day's worth of data could be wrong. You have to be very, very fearful. You have to be anxious. You have to be anal in order to do a good job with this kind of technology. And in general, that's true about science. You can't be cavalier when you're making measurements. It's not on the list, but one of the biggest limitations of a total station is that you have to have a good line of sight. In other words, from the total station, you have to see the prism. So if you're in the middle of a forest, you can't use a total station very easily because you won't have a direct visual line of sight. On the other hand, if you're out in an open terrain or a terrain where you can raise the pole above the height of the vegetation, then you can do a pretty good job. And finally, if you want to get into a real-world coordinate system, you've got to have benchmarks. And for me, that can be quite a big limitation because a lot of times I need to be in a real-world coordinate system and I can't get it because I'm out on some river somewhere and there isn't a National Geodetic Survey benchmark anywhere in sight. That brings us to what's becoming more and more of a gold standard, which is Global Positioning System. Simply for its universality to be used anywhere in the world and get a pretty good position accuracy. So GPS, as we call it, is a device that consists of a receiver and an antenna, usually with the antenna mounted on a pole, as shown here. And instead of having a line of sight to a total station instrument or an auto-level instrument, you have to have a sky line of sight to satellites that are orbiting above you. So you can't be in a dense forest or you can't be inside a building. You have to be somewhere where those satellites can be sending signals that are received through the antenna to the receiver. And in this case, the receiver is in this yellow hip sack that this person has. So with a GPS, you go to a location, you hold the pole or your handheld unit at the location you want to know its geographic coordinate, and then you record the position through time. So unlike a total station, which is wicked fast, in this case, you've got to record for, preferably a good 5 seconds. Depending on the quality of the instrument, you may need to record for 3 to 5 minutes or longer, depending on the circumstances. So a GPS, it inherently works within a coordinate system. It's essentially a spheroidal coordinate system around, an ellipsoid of the Earth, I should say, and that's usually the WGS 84 coordinate system. So then from there, you have to convert that data from geographical coordinate system, which means like the ellipsoid, to whatever local or national coordinate system you want that's typically on a plane, such as the state plane system or UTM or Cal Albers or something like that. Okay, so the best utility of the GPS is if you need to move around to a lot of different locations where you're not going to have line of sight or a benchmark nearby. So when you get to places where a total station doesn't work well, then that's when the GPS steps in. The GPS can work and overlap quite a bit with the total station if you have what's called a survey grade GPS, which I'll talk about more. And if you just are willing to spend a little bit extra time observing a point rather than moving as fast as a total station can move. The cost depends entirely on the precision and accuracy that you want to get. GPSs, of course, they're like integrated into all kinds of devices for low dollar amounts that you don't even notice, but the accuracy isn't very well, and there's a lot of software massaging that goes on for how they're being applied. On the other hand, if you want to have the most precise survey-grade system, you're talking basically a $50,000 system. So the advantages of a GPS are that it's really highly automated, and it's pretty fast. I mean, compared to an auto level, let's say. Many features built into it, so you don't have to make a lot of manual decisions. The accuracy is going to depend on the atmospheric conditions and the configuration of satellites, and I'll say more about that in a few minutes. And one of the really cool things about it is because you're observing through time, you get a measurement of the precision that's there. And if you do have benchmarks, you can add in an estimate of accuracy as well. The disadvantage is there can be a steep learning curve. It's really no faster than a total station. And you need to have a line of sight with satellites. So if there's a lot of buildings around you or trees, then you're going to run into problems. So let's look deeper because GPS is just too important to not understand more of the theory at this point. So in the United States, we have what's called the GPS Satellite Constellation. It's a group of 24 satellites that orbit the Earth every 12 hours. 4 satellites are kept in 6 orbital planes. And independent of this American system, Russia has its own system called GLONASS. It is possible, like modern devices are capable of receiving the signals from both the United States and Russian satellite constellations, at least for now. That's the best quality you can get, is to use both. If you want to get a 3D position, you need to see at minimum 4 satellites. But realistically, you would prefer to have 8 to 10, and the more the merrier, and I'll be showing you why that is. So here's how GPS works. All GPS is really doing, and it's core. Of course, it can do lots of things, but essentially it's measuring distances. It's measuring the distance from the satellite above to your antenna. Let's pretend this is my antenna. Okay, it's measuring that distance. So let's say I'm at this point, okay, and the green, red, blue, and purple lines here are the distances between 4 different satellites. That's all you're going to get, essentially. And depending on the quality of clocks and other things, you get a better or worse measure of distance. So now I know, based on tracking systems, I know where satellite 1 is, I know where satellite 2 is, I know where satellite 3 is. Well, if I know the distance between me and satellite 1, then that's essentially a radial or a sphere, essentially. I'm somewhere on a sphere, that known distance away from satellite 1. So let's just pretend it's a 2D problem for simplicity. That creates this radial circle. Okay, now from satellite 2, I'm this distance from the receiver. That creates this circle. And from satellite 3, I have this circle. So in theory, with just 3 satellites in a 2-dimensional plane, I can nail down that I'm either at this position, but no, I can't be at that position. With only 2 satellites, there's 2 positions. With 3, it locks it in that I can only be in that place. However, the reality is we're not talking about 2-dimensional positions, we're talking about 3-dimensional positions. And so to get that accurately, you need to over-predict the problem and have more satellites, typically a minimum of 4. In order for this system to work, we have to expect the federal government to put out a lot of money and effort to maintain this kind of system. There's a lot of infrastructure that's involved. So for example, we have to have tracking stations, a control station. We have to be able to track all of these GPS systems. They have to each have really precise clocks. Our receivers have to have really precise clocks. And we have to have information about what's going on in the atmosphere. All of this information is used by your local receiver as you're moving around to figure out its positions. But there are also ways to go home onto your computer in the office and improve your accuracy by taking advantage of better information as things are processed through time. So what controls the accuracy of the results you get? Well, because we're measuring distances, it's everything that affects distance. And we're measuring distance by sending a signal. So the signal is moving at a speed. We have to make an assumption about what that speed is. And we have to be able to measure the time at which the signal is sent and the time at which it is received. So clocks become very, very important. Knowing the positions of the satellites is very important. And those are all influenced as well by what's going on in the atmosphere. Also, if you have a receiver, let's pretend my head is a receiver, okay? Now I've got, unfortunately my head looks too much like a receiver, but anyway, so the signals are coming right here into my receiver, my antenna, I should say, sorry. The antenna for my receiver, which is inside. So the signal's coming in, great, so I have a direct shot. Now what happens if a signal bounces off those bushes there and then hits my head? Or bounces off the ground and reflects up into my head, right? So I'm not only receiving the signals straight from the sky, but I'm receiving all of the signals that the government is pumping into my head from all directions. So the problem is that we need to have a very good antenna that's designed to try to block out as much of that unwanted bouncing as possible. That's called this multipath interference problem. But most of all, the main limitation in accuracy is something called position dilution of precision, PDOP. Okay, well, precision is what we want, so dilution of it can only be bad, and it's with respect to the position. So first, of course, if I have two satellites that are literally right next to each other, the distances I get are basically the same information. It doesn't help. So in this picture on the left, I've got 4 satellites that are relatively overhead, and so my circles are going to be relatively similar. Now look at this other one. Here I've got satellites with different distances away and at different altitudes above me. And that is going to give me significantly different circles to cross-check things. Notice that there is no way, because the Earth is underneath me, that I can get the ideal solution of having satellites all around me. They can only be above my head. They cannot be below me underground because the Earth blocks the signal. So how can we improve the accuracy given these fundamental limitations to the system? The first is through averaging. So here's 2 examples. So imagine a bullseye. The center of the bullseye is our true position. With a low-cost GPS unit, every time we sample, we're not moving. We're just holding in one position. But the GPS is going to say, I'm here, no, I'm here, oh, I'm over here. And so that's this sort of like shotgun blast that's around here. When you have a situation like this, you can get high accuracy, but it's going to be low precision. That means that you could have points that are all over the place, but when you average over a very large number, you're very likely to get the right answer here in the middle. It's basically like if you have a lot of people guessing something, every person might be wrong, but when you average across all those guesses, you surprisingly get a pretty accurate result. So that might be a low precision, high accuracy result. And so that's why collecting data over a long period of time is very important for GPS, and it's one of the main limitations of this technology. On the other hand, if you have a very expensive, like a survey grade unit operating, talking to a base station, as I'll talk about in a moment, you can get very precise measurements. That is, each observation will be close to true, and if you average through time, again, you'll get a high accurate result. The fewer samples you collect, then the more risk there is that one individual point will be far off the mark. So spending more money increases your chances of being close to the mark, but by averaging through time, you can substitute time for cost and get a pretty good answer. Okay, so point averaging is one method. The next is a method called differential correction. This is where we're going to take the raw reading that we get from the mapping we do in the field, and we're going to improve it. So let me show you how that works. Imagine that you have what we call a base station location. So this plus symbol is a benchmark with known coordinates, like the National Geodetic Survey has gone out and it's told us here's the coordinates at that point. Now we take our GPS and we put it on the point, but the coordinates we get back from the satellite is not there. It's over here. Well, we know that is wrong. Okay, we've put our instrument here, we know the coordinates here, but it's told us we're over here. This tells us the undesirable shift, but it's a known amount. Now imagine if at the same time one of our buddies was out with another instrument and they're standing at this green point. They take their measurement, but they say, no, you're over here. Well, in the field, we don't know that we're wrong. Okay, at the base station we know because we're told already what it is. In the field, we're trying to find out the coordinates at this green point, but we're given this red point. Well, what we can do is we can take this error or shift from the base station location and apply it at what we call the rover location in the field and move us over to here and say, you know what, this is the uncorrected position, but I'm going to apply the offset that we saw at the benchmark and I'm going to move us over here. This is called differential correction. It can be done in the field in what we call real time, using real-time kinematic GPS, where a base station is talking to a rover unit, usually through a radio network. It can also be done later on, like you can just collect your data in the field, come back to your office and say, okay, on the computer, where are there any base stations that are in proximity to mine? And then I'll use their corrections. And so another benefit of our public good is that people all over the United States operate these base stations and get these errors. And it's almost like a few clicks to apply a correction. The further the base station is from the rover, the less useful the corrections are because it's going to be experiencing different atmospheric and satellite, atmospheric conditions and satellite configurations than what the rover is experiencing. Okay, so that's what we call like post-process differential correction versus real-time differential correction. Now, ideally, when I'm post-processing for what I would call mapping grade, like sub-meter to meter resolution, I'm looking for something that's 30 kilometers or closer. However, if I need something at centimeter level accuracy, then I want something 5 kilometers or closer of a survey grade, or I want to set up my own local benchmark that's going to be within 1 kilometer from where I'm measuring. Okay, so some of the different types of GPS receivers. Of course, your cell phone may have it, but a very low cost, built into cars, or these typical recreational mapping grade units are for hiking, boating. These are usually, they claim to be accurate to within 1 meter. They're typically accurate to within 10 meters in the horizontal, 30 meters in the vertical, but they use software to say, hey, I have to be on a road. Like, I was driving over the San Francisco Bay Bridge, and on the car, it had me going over the water when I left the bank and when it started going over the bridge. But it quickly realized you can't be a boat. You're not the bat car, right? You can't switch from a car to a boat. So it actually snapped me over to where the road was and had it on. Not because the GPS was right, but because it had software to fix that. A mapping grade unit is something like is shown here, like a Trimble Geo XH, something like that. This is going to be accurate to within 1 to 3 meters in the horizontal, 5 to 10 meters in the vertical. Why is vertical worse? Because there's nothing below you, right? You can't have any satellites below you, so the satellites are always going to be above you, and so that makes vertical worse, whereas horizontal can be spread all around. A mapping quality unit is in the 500 to 5,000 plus range. The next level up are real-time differential units. The price of these has come down, so they're kind of in the $5,000 to $12,000 range, I'd say at this point. These are ones, actually now I would say they're getting down to like a 10 centimeter accuracy, but again, a lot depends on how close the base station is that you're using for that. And really the cream of the crop, the gold standard best technology is real-time kinematic. What you see here is a unit in which we have the antenna and the receiver is integrated into that. There's no backpack the way that there is in this other unit. There is an independent data collector, but it has a lot of power and utility in that. You can also see there's an antenna. This is a radio antenna that is talking to the radio base station. In some cases, that even could be talking to the internet. If you have a cell phone connection on here, you could be getting an internet-based real-time correction. One of these units tends to be in the $15,000 to $30,000 price range for one. Now, if you want to set up your own base station, you need two, and that's going to put you, and then you need radio equipment and a license from the FCC or all kinds of stuff. So then you're talking more about $40,000 to $60,000 for a complete system. Okay, we're going to switch gears from the land to the water. Obviously, anything that you can walk in or wade into, then you can measure. It doesn't matter whether there's water there. What if the water is too deep or too fast or both? Then what do? That takes you to the realm of what we call echo sounders. This is a setup. There's me in a simple boat. I've got my RTK GPS here, so the antenna, the receiver, the data collector, and then I have an echo sounder. The echo sounder has its own receiver, which is this box, and then underwater, you can just make out a little bit of black there. That's called the transponder. And so what happens here is this is a device, and all it does is it just sends a sound wave down. It pings off the bottom of the river or lake or whatever you're in and comes back. So in the same way that the satellite sends a signal and measures a distance, an echo sounder is measuring, it's like an echo, right? It's measuring the time it takes to travel through water. You have to specify the temperature, and based on the depth it's going to, you're getting, it can say something about pressure or other, the density of water essentially. You also have to specify whether you're in fresh water or salt water. The farther you go, the bigger the area that it's pinging off of. So a relatively low-cost sensor, such as the one I'm using here, might end up with a fairly big area of the bed that it's echoing off of, whereas a higher-cost one might stay as a finer beam straight down with a narrower spread, because sound waves spread as they go through distance. And what you can see is that I've got all this integrated. So my GPS can talk to the echo sounder through Bluetooth. It takes the depth and it adds it to, so the GPS is getting the elevation at the antenna, then it's subtracting the length of the stick down to the transponder, and then it subtracts the depth to get to the bed position. So with this device, I can just kayak around or motorboat around and get your X, Y, Z coordinates. Compared to walking, being in a boat is really fast. On the other hand, you can't do point averaging. You're getting one GPS point per second, and that's going to go with the value for the echo sounder at that second. So there is some GPS inaccuracy, and that's why it's essential to do this with an RTK GPS, not a differential grade GPS, if you want to get a good map. You can do this with a mapping grade GPS. It's not something that I recommend, but it is possible if you don't really care about getting the topography right. So of course you need to know how to operate whatever kind of boat. You have to pick the boat. You have to know something about the river or lake terrain to operate safely. You have to know how to use GPS. The echo sounders itself, relatively straightforward. A few little tricks of the trade. There's definitely problems come up whenever you're working around water. Also, it's just giving you a point as you move along the line. Even if that's 1 point a second, it's just basically giving you that line, or dots making a line. It doesn't have to be a straight line, but that is fairly limiting. An echo sounder might cost anywhere from $4,000 to $20,000, depending on how sophisticated it is or what other kinds of corrections it has. Some of them have the ability to adjust for roll or pitch or bobbing up and down, for example. So that's the essence of a single beam echo sounder. Now we go to the big brother here, multi-beam echo sounder. So in a multi-beam, instead of just sending out one beam, as the boat is moving along its line, it's sending out, say, 100 to 200 all at the same time in a swath. It's still discretized into points, but as you move in one direction, we're getting a profile across the boat as we move. And so that you could see in this example image how if you have a lot of beams, then you're getting a really detailed map. And I'll just show you an example of that. This is a relatively narrow canyon. We have a quarter-foot spacing here between points. And so what you can see is, as we're going down, I know you can't really get a sense of scale, but the width here is, I don't know, like, 100, 150 feet, something like that. And so as we go down here, you can see we can make out individual boulders and cobbles on the channel bed. So this is very automated, very fast. Of course, it's not for wadeable conditions. It's extremely accurate. Of course, you have to also tie into an RTK GPS. It's relatively expensive. If you were going to buy this, it might be $50,000 to $150,000. But you could also rent the system, and then it actually becomes quite affordable. Again, you have to know how to operate the boat. This has a really steep learning curve. This has customized software. So it's really not something like I'm not going to go out and learn how to do that. But what I'll do is I'll hire somebody. And so I know enough of when and where and how to use it. Like if me or someone, one of my collaborators is driving the boat and we have a professional hydrographer operating the multi-beam, then we can map very effectively working as a team. Okay, we just have a couple more of these technologies. The next one is something called Airborne Light Detection and Ranging. So remember that the total station sends out an infrared wavelength light that reflects off the prism. Well, what if you had a light that didn't require glass but could reflect off of any natural surface? That's what LiDAR is. LiDAR is a very strong laser that's capable of bouncing off. So it's just like an echo sounder, but with light instead of sound. So you fly an airplane or a helicopter over the ground, and it's something that it's just shooting one dot, but it's scanning very fast across the plane. So you get this like looks like a fan going across. So as the plane moves, it's scanning across, and it's making a map that looks very similar to MultiBeam. Today we have about 32 points per square meter, but this number is changing very fast to get ever more dense points. The vertical accuracy of a position is about 5 to 30 centimeters, so it's relatively coarse compared to total station or our RTK GPS. However, it's wicked fast. I mean, you're flying an airplane fast. You can map, it can map the top, the inner structure, and underneath vegetation. So like if this shrub behind me, it's very unlikely to pass the laser all the way through to the ground hidden underneath. But this single tree that's behind me, I'm going to tilt this up. It's very likely to give me many returns in the canopy as well as pass through and hit the ground below. So there's really a lot of value that LiDAR provides, not only for getting the bare earth topography, but getting the structure of vegetation. What happens when LiDAR hits the water? Well, commonly this is a near-infrared or red light, and as a result, it reflects off the water surface, and therefore it maps the water surface. So this typical airborne LiDAR that uses red LiDAR cannot map through water. However, there is a different LiDAR called green LiDAR that where the green light can penetrate through water. And if the water is crystal clear, and if the water doesn't have air bubbles and a lot of junk in it, turbidity and debris, then it can pass through and hit the bed and come back. So if you pair a red LiDAR package with a green LiDAR package, you can map everything. And green LiDAR, it's still an emerging technology. It has a lot of limitations, but it's emerging relatively fast. Of course, in order to use LiDAR, you either have to have a fair amount of money, thousands and thousands of dollars, or you have to hire somebody else. You have a lot of money to hire somebody else, or you better know how to fly your own airplane and operate your own LiDAR system and GPS system and all that. Very few people are going to do that on their own. There are companies out there that will do airborne LiDAR mapping for you. They can follow rivers, they can map whole mountains, whatever you want. The cost just depends on the size of the area, and the minimum cost is just an inescapable starting fee because you have to get the airplane to your location. You're basically having a pilot and a plane and a staff on site, so there's that cost. Once you're in an area, the more land you map, then the more efficient it becomes, so the cost per point goes down. The other thing, when you map an area with LiDAR, you could be getting 100 million to 1 billion points. So then you have to be prepared to manage millions and millions of points, and that becomes an effort unto itself. Here's an example of a map that includes both LiDAR and echo sounder data. The deepest part of the channel, the dark greenish blue, is echo sounder, but all of this light green, yellowy, and brown areas are all mapped with LiDAR. So for example, like you can see the slope break here. It's mapping all these rip-rop groins that are out here. You can see these hills, you can see roads that are in here. There's a lot of detail that you get from LiDAR. There is a land-based version, so instead of mounting this on an airplane looking down, mount it on a tripod looking to the side, and here's some gullies along the side of a road, and you can see, it's just scanning across, shooting lasers up and down and across, and look at the incredible detail. So, here you could get 100 points on an individual pebble if that's what you want. The accuracy is in the millimeter range typically, just depending on how far you're scanning. You can have 10 to 10,000 points per square meter. Once you set it up, it maps very fast. It can map the top of this inner structure and through vegetation. It can't map through water again unless you have a green LiDAR. The biggest problem with ground-based LiDAR is it can't see behind an object. So if I was standing where I am and I scanned behind me, it would hit the tree, like the trunk of that tree there, my thumb is now on, and there would be a shadow behind that. So what you have to do is then get the LiDAR and move it around to a different place and catch the shadow area. So here, there might be some shadows in this image behind each one of these sort of like hill slope noses that are poking out. But this is a pretty ideal setting. There's not a lot of shadow in this image. A terrestrial LiDAR costs $80,000 to $150,000 to buy. Terrestrial LiDAR is becoming widely used in forensics, crime scene investigation, as well as in earth science to really see the details of processes at the millimeter to centimeter scale. Then we have something that some people call poor person's LiDAR. It's what we call structure from motion. Instead of using a laser scanner, what you do here is you just take your cheap little camera and you click, 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 lots of photos from different positions. Here's an example where we have a camera from 3 different positions looking at an object. The structure from motion, the motion is moving the camera to different locations. The structure is a software reconstruction of where the camera must have been in space to have taken the photo relative to the other photos, and then the structure of the object that you're photographing. So here's an example of a photo reconstruction of another gully. It's a little bit hard to see because of the grayscale, but you can see the gully coming through here, and then you can see this box that's been put out for scale. Structure from motion is susceptible to shadow effects, like you can't see behind this object, but you can do structure from motion from a drone or a blimp or a quadrocopter, so getting it from the sky, then you're going to have very little shadowing effect. This is really cheap. You have to have software that can process that, and there's more and more software packages. This is the fastest growing technology that we have for Earth surface and hydrology today. It's just changing so fast, so I hate to say too much about it. It's going to give you a relative coordinate system, but if you have pre-established benchmarks in your photos that you GPS, usually, then you can get those coordinates. Okay, so let me just summarize. There are many different technologies. The simplest, a tape measure. The most sophisticated, airborne or terrestrial LiDAR. There's a lot of trade-offs that are here. Cost, learning curve, doing it yourself, cheap, like structure from motion, or paying a professional so you could focus on hydrology and let them do that work. Unfortunately, the technology is changing, so you have to keep up with the methods on a regular basis. Some methods are good for covering large areas, like airborne LiDAR. Some are for working in really shallow or tight areas, or in a forest. They have a range of how many points they give you, what kind of data, the quality, precision, accuracy of the different results. So that's the presentation on geographic positioning systems. I've covered a lot of ground, and as always, I talk very fast. So luckily, you can pause, rewind, and review the video podcast. We'll look at several of these technologies in class, in lab, and on field trips. So we'll play with this stuff. So don't feel like you have to learn all this just from this video podcast. This provides you an introduction. My advice is that you watch this first, as you've now done, play with everything, and then come back and watch it again to really understand now that once you've had that experience of playing with it in the field.